Hey, welcome back to Mr. P Helps with Precal. This is Unit 2, Chapter 2, Lesson number 6. We are solving exponential and logarithmic equations using Newton's Law of Cooling. I'll start off with a warm-up just like the last video. So we're multiplying 40 times increasing rate, so that's 1 plus 0.23 to the X amount of years. Initial value of 300 being multiplied by decreasing, so that's 1 minus 0.08, which would be 0.92, every 6 months, which means twice a year. So that's to the 2x power because it's twice per year, if x is the amount of years. You are investing $1,500 in a fund that is compounded monthly with an interest rate of 2.5%. So that's 1,500 times 1 plus 0.025 divided by 12 because it's monthly, 12 times a year, and then to the 12 times X amount of years. We don't know the amount of years. And there you go. There's a model that represents each one of those equations. So Newton's law of cooling is this. So Sir Isaac Newton found out that the speed at which things cool or heat down or heat up changes depending on the medium. So this is the temperature of the air or whatever the substance is that you're putting the item into. And T of 0 is the temperature of the item to begin with. And then T of T is the temperature of the item after T amount of minutes. So T right here, the small t can be anything. So you may or may not already know the T, and you're going to solve for the rest of the items. T temperature of the medium, temperature that it was to begin with. Now, we have to assume that this equation only works if the temperature of the medium stays the same. So, in other words, if you put a very hot object into a small confined box, then the air is going to actually heat due to the item heating up the air that's surrounding it. So we have to assume that it's not going to affect the change, not going to affect the temperature of the medium. All right, so with that said, a hard-boiled egg is 96 degrees, placed in a bowl, water is 16 degrees Celsius. All right, and then it tells you that the constant is 15. So write an equation. So we're going to simply just plug these numbers in, which happens to be, so T sub T after T amount of time, which we do not know, equals the temperature of the medium, which happens to be 16 degrees, plus the beginning was 96 degrees minus 16 times e to the 0.15 times t amount of time. There's the model. Now that we know that 5 is the time, so I'm going to put 5 in for t and solve. So the time after 5 minutes is equal to 16 plus 96 minus 16 makes 80 times e to the 0.15 times 5 amount of minutes. So I can just simply put this into the calculator. So I have 16 plus parentheses, got to turn the calculator on, 16 plus parentheses 80, and I'll show you on the screen here in just a second, e to the power of 0.15 times 5. So we're looking like something like this in my calculator, and then I press enter, and I'm told that T of 5 is 185 degrees, give or take. I'm going to put about 185 degrees. What is the temperature of the, what temperature will the egg approach? So the egg is going to get closer and closer to a temperature of 16 because that's the temperature of the medium. So the egg's going to get closer and closer to that temperature. It's never going to quite, it could, I guess technically, theoretically, reach it perfectly, exactly, but it's never going to get less than that. So once it reaches that temperature, it's not going to change unless an outside source changes it. A cake is removed from an oven and its temperature is modeled with this function. Determine the temperature of the cake when it's removed from the oven. Okay, so remember the formula is the temperature it started with minus the medium equals this number right here, which is 285. So then if I add 65 to both sides, then x must be 350 degrees. Determine the temperature of the cake after 10 minutes. So if I put 10 in for t and solve, so that's the temperature after 10 minutes equals 65 plus 285 times e to the negative 0.2 times 10. Once again, I can just simply put this in the calculator and then press enter and it'll evaluate it all for me. So 65 plus parentheses 285. Technically, I guess I don't need those parentheses. And then e to the power of negative 0.2 times 10. All right, and I'm getting about 103. So the temperature after 10 minutes is going to be about 103.6 degrees. If a perfect time to eat the cake is at 100 degrees Fahrenheit, how long will it take for the perfect time? So now we know 100 degrees is the the temperature after T amount of time. We don't know what the time is, though. So equals 65 plus 285 times e to the negative 0.2 times T amount of time. We don't know the time, so we're going to solve it. Minus 65 from both sides gives me 35. Then divide by 285. Then that's going to cancel this out. So that gives me 35 over 285 equals e to the negative 0.2t. So now I'm going to do natural log of both sides. And once I do that, then I'm going to have to divide both sides by negative 0.2. And that's what I'm going to put into the calculator. So natural log of 35 divided by 85, end parenthesis, divide that by 0.2, and that's going to give me, okay, it should have been negative 0.2, shouldn't have. Divide that by negative 1. So it gives me 4.4. I know I just did this pretty quickly. It might be, hopefully that's not wrong. So natural log of 35 divided by 85. Oh, it's 285. That is wrong. Okay, so my chicken scratch handwriting reminded me that this is not 85. This is 285. So let me try that again. So natural log of 35 divided by 285, end parenthesis, divided by negative 0.2. And that's going to give me about 10.5 minutes. So T is about 10.5 minutes. All right, what is the temperature of the room? The temperature of the room is 65 degrees, and I know that because that's the temperature of the medium. The medium here is the temperature of the air. All right, so one more question, and these two questions are the same. Okay, so two more questions. Hopefully I'm going to make it. Yes, I will. Determine the temperature of the cookies when it's removed from the oven. Use just mathematics. Okay, this question is actually exactly like the previous question I just did. So you know what? I'm actually going to skip. No, it's not because we got to solve for K on this one. Okay, I'll do it. So this is going to be X temperature minus the 73 degrees medium equals that 312. Because it's already been simplified, add 73 to both sides, and you get 385. If the cookies are 200 degrees after 8 minutes, determine the value of K. Okay, that's something we haven't done yet. We haven't solved for K. So 200 is the total, equals 73 plus 312 times E. Let's move me to the K times, we don't know K, times 8 amount of minutes. Okay, so minus 73, that's going to give us 127 to the 8K, and then divide by 312. All right, and then we're going to do natural log of both sides. So 127 over 312, then natural log to get rid of that base E, and then divide all of that by 8. So natural log of 127 divided by 312. Then divide that answer by 8. And that's going to give me a K of negative 0.112. All right, but the equation is negative KT, so technically the K is positive 0.112. Based on this model, what's the temperature of the room? How does it relate to the graph of the function? Well, 73 is the horizontal asymptote. And the reason why is because this graph is exponential. It's decreasing like this. And the reason why it's decreasing is because it's negative KT power. Remember, negative powers go down like in a previous video. And it's never going to reach that horizontal asymptote of 73, no matter how many minutes it's been. So, like I said before, the temperature of an item is not going to get colder than the surrounding air. I mean, that just doesn't make any sense. If you take a hot pie out of the oven, put it on your counter, it's never going to get colder than room temperature. It might reach room temperature, but it's not going to get colder than that. If you want it to be colder than that, you got to put it in a refrigerator. Because it's just going to stay room temperature. That's just common sense, honestly. This question is a lot like the last question, so I'm just going to do this last one. A cup of coffee is cooled. So look at this question as like two parts. There's first sentence that says that it's cooled down to 92 degrees and It started at 92 degrees. It cooled down to 50 degrees. It took 12 minutes to do that, and the surrounding air is 22 degrees. Then we'll solve for K, and then we'll worry about the second sentence. All right, so we know what the temperature was at the end equals the temperature of the surrounding air plus T of 0, which is 92 degrees, minus 22 degrees times E to the we don't know K times 12 amount of minutes. All right, subtract 22 from both sides, and we get 28 equals, this ends up being 70 times E to the negative 12K power. Divide both sides by 70. That cancels out here. Then do natural log to cancel out the E. Then divide it by negative 12. And that's the formula for K. So I put that in my calculator. And I really wish my dog would stop barking. 28 divided by 70. And then divide that by negative 12. And that gives me about 0.076. Now, I'm going to read the second sentence. It says, how long will it take for it to cool to 30 degrees? Well, if 30 degrees is the temperature after T amount of time, we want to figure out, well, how much time is this? What would this T have to be? Equals, temperature of the medium is still 22, plus, this is still, temperature at 0 is still starting at 92 degrees. It's still the medium, so this is really the same thing, times E to the negative 0.076 times T amount of time. All right, subtract 22 from both sides, and you get 8 equals 70 times E to the negative 0.076 T. Divide both sides by 70, then do natural log of both sides, then divide both sides by negative 0.76. All right, so natural log of 8 divided by 70, end parenthesis, divided by negative 0.076. So that's what you can see, what I put into my calculator, press enter, and I'm getting the time is about 28.5 minutes, 28. All right, thanks again for watching, and please give it a like to help you learn something about solving solving equations, and when Newton's law of cooling is applied. All right, have a great day.